Hello, this is the second lesson of Topic 4. Topic 4 is an introduction to digital systems, and the main objective of Topic 4 is to learn several ways of representing a logic function. We have already seen three ways of representing a logic functions. The first one is the more straightforward, I think, that is the algebraic way, just writing the function is equal to x, for example, multiplied by y plus z, the equation. Another way is the interconnection of logic gates. We can connect AND, OR, NOT, inverter, etc. and have the function implemented with logic gates. It's another way of representing a function. And we have already seen that we can implement function using CMOS and NMOS circuits. So if you remember, connecting transistors in parallel or in series, we can implement a logic function. So they are three ways, and we are going to see more ways in the topic. Finally, when you finish and you study the topic, you have to be comfortable to master this change between one representation and the other. That's the main topic. The main target of the topic. In the last lesson, we started seeing the Boolean algebra, and I told you that the Boolean algebra is the mathematical basis, the mathematical framework that is going to give rise to the appearance of the logic design theory. We are going to use the logic design theory to design and to analyze logic circuits, digital circuits. So we have a lot of Boolean algebras, but the switching algebra, the one that we are going to use, is a Boolean algebra that satisfies some kind of requirements. Specifically, is a Boolean algebra that satisfies the 6 axioms of Huntington and whose elements are 0 and 1. We already saw the 6 axioms of Huntington that are like rules that you have to learn. Okay, the identity elements, the commutative property, the distributive property. Be careful with this, apply to the sum, because we don't have it in the traditional algebra that we use in previous studies. We have the complementation action, and a consequence of applying this action is the appearance of some theorems that we have to learn. The duality principle is really useful because we can extract the dual theorem and the dual action applying it. Remember that we can obtain the dual expression changing the logic sum by a logic product and changing ones by zeros and vice versa. We already have the idempotent law, the involution law, the absorption law that is quite powerful because we can remove a term in the expression, the associative property, the consensus law, and the De Morgan's law. We are going to use these actions and theorems to manipulate algebraically the logic functions. We already saw the logic gates. We have here 3 basic logic gates, but you have in the end of the slide the rest of the logic gates. Remember that we have as well the XOR, the NAND, the NOR, the XNOR, etc. So you have them there. Just check it, okay? And you know that every logic gate performs certain operation over the operands at its input. So now we are going to see some definitions that are important when using the Boolean algebra. We are going to define a constant over V as any element of V. This is really simple to understand. A constant is going to be either 0 or 1. More things. A variable is going to be a symbol or a noun whose value is going to be finally 0 or 1. So a variable can be x, can be y, z, the letter we invent, the letter that we choose. And finally, they are going to have a value in the set B. The concept of literal is important because we are going to use it later. A literal is going to be either a constant or a variable. So a literal can be, for example, 1, 0, x, z, etc. And we have a Boolean function as the following application. It's quite simple, but I'm going to write a little here to develop the concept of a function. So a function is an application of the set b rise to n in the set b. For example, if we have this function b rise to 3 into the set b, it means that we have a function of 3 variables whose result is going to be in b, and b is 0 and 1. So, for example, I can invent this function x logic product e logic sum complemented x logic product complemented c. So this can be a logic function with 3 variables, and you can imagine that we have that each variable is a switch that we can press. If we activate the switch is 1, and if we don't activate the switch is 0. And certain combinations of these switches can turn on a bulb. Okay, so that's a logic function. So if you remember, we saw as well a way of representing a logic function that is the truth table. The truth table is a table that contains all the possible combinations of the inputs. If we have 3 variables, we can have 2 rise to 3 combinations, 8. So I'm going to write all the possible combinations. You'll learn to do this fast, okay? It's just experience. Sorry. So, how do I know the value of the output for every combination? I can replace each combination into the function. For example, for the first combination, x, y, and z are equal to 0, 0, 0. So 0 multiplied by 0 plus complemented 0 multiplied by complemented 0. I'm just using this function replacing the values. So I have that this is 0. Why? We can check. I'm doing it fast, but you can check the laws. The idempotent law. Something multiplied by itself is just something. So using the idempotent law, we have that 0 multiplied by 0 is 0. This is 0 negated. 0 negated is 1. So we have this. And using again the idempotent law, we have, and this is the logic product. So this is 1. So for this combination, the output is going to be 1. For example, for the combination 5. 5 in binary is 1, 0, 1. We replace the values in the function, and we have the following. This is 0 using the null element theory. Something multiplied by 0 is 0. So this is 0, and this is, sorry, this is I have changed the cursor. Sorry. This is the complementation of 1 is 0, and this is 0, and 0 multiplied by 0 is 0. So we have this. So for 5, for the combination 5, the output is 0. As you can see, this method is really slow because we have to check every combination. If we have 4 variables, we are going to have to check 16 combinations. So we are going to see better ways and faster ways to go from the algebraic function to the truth table and vice versa. Okay? This is one of the targets of this topic. So we are going to come back to the slides and we are going to continue. So we are going to continue with the definitions. These definitions are really important. You need to have this concept really clear. Okay? Here you have the formal definitions, but they are really easy to understand. So I'm going to give you an example to help you understand what these definitions mean. So we are going to define a product term as either a literal or a product of literal in which each variable appears at most once. So imagine that we have a function of 3 variables. The variables are x1, x2, and x3. I'm going to give you examples, and you have to check if these examples are or not product terms. Is x2 a product term? Yes, it's a product term because it's a literal. Remember that a literal is a constant of a variable of the function. So that's a product term. Is 0 a product term? Yes, it's a product term for the same reason. It's a literal. A literal is a constant or a variable. Is, for example, x1 plus x3 a product term? No, because it's not a literal and it's not a product. It's a sum. It's not a product, it's a sum. So this is not a product term. And this is a product term. Yes, it's a product term because it's a product of literals, a product of variables. It's a product term. This is a product term. Yes, it's a product term because it's a product of literals. It doesn't matter if one of the literals is a variable that is complemented. It's the same. It's a product term. And this. This is not a product term. Why? Because the literal x1 appears twice. And to be a product term, each literal, each variable has to appear at most once. So this is not a product term. I think that is quite easy what a product term is. What's a min term? Min term is a specific product term that is composed for all the variables of the function. And I'm going to give you a sample. This is quite easy to understand as well. So if we have the function as before, this function with 3 variables, is this a product term? Sorry, a min term? Yes, it's a min term because it's a product term in fact is a product of literals, but besides, in this product term, all the variables, all the functions appear. So this is a min term. Is this a min term? No, it's not a min term because we don't have x3 there. We don't have x3. So it's not a min term. And this. Is that a min term? No. Why? Because we have all the variables of the function, but this is a sum, not a product. And a min term is a product term in which all the variables appear. So it's not a min term because even if we have all the variables, we have a sum there, not a product. So now we are going to define the disjunctive normal form. The disjunctive normal form is a way of representing a function. It's an algebraic representation of a function. So in the exam or in an exercise, you can find that you have to obtain the disjunctive normal form of a function. It consists in the sum in a single product term or the sum of various product terms. I'm going to give you some example. Imagine that we have a function of 3 variables. Imagine that the function is this, x2. Is that a disjunctive normal form? Yes, because it's a single product term. x2 is a literal, so it's a product term. So it's a single product term, so it's right. What happens if the function is, for example, complemented x2 plus x1 multiplied by x3 negated? Is this a disjunctive normal form? Yes. Why? Because if the sum of various product terms, x2 negated is a product term because it's a literal. S1 multiplied by complementing x3 is a product of literal. So we have here the sum of various product terms. So this is a disjunctive normal form. And this. Is this a disjunctive normal form? No. And why? Because this is not the sum of various product terms. This is the product, not the sum, of a product term multiplied by something that is not a product term. Okay? So, no. This is not a sum of product terms. I think that is easy to understand, but you have to study to learn it. In this point, you can see that I have used red for products, and now we are using blue. And I have used red for products and blue for sums. We are going to have here the dual definitions of the product terms that are the sum terms. Are the same, but the dual of the product, that is the sum. So I'm going to delete this to have more space. Okay, so what is a sum term? Just following the definition as before, but applied to the sum, is going to be a literal or a sum of literals in which each variable appears at most once. So I'm going to give you again examples. Is if we are using the same function of 3 variables as before, for example, is this a sum term? Yes, it's a sum term because it's a literal, it's a variable. Is this a sum term? Yes, because it's a literal. And this? Yes, because it's a sum of literals. And this? No, because x2 appears twice. And this? No, because this is a product of literals, not a sum of literals. In fact, this is a product term, so it's not a sum term. We are going to define a max term as a specific sum term in which all the variables appear at most once. You can see that this is the dual definition of the min term, but using the sum. So, for example, is this a max term? Yes, because it's a sum term in which all the variables of the function appear. And this? No, because x1 is not in the sum. So this is a max term. And what's a conjunctive normal form? It's a way of representing a function algebraically, but consisting in a single sum term or the product of various sum terms. For example, can be this, because this is a sum term, but can be as well this. Because here we have a product of three sum terms. So I think that this is quite easy, but you have to study. It's important to have this concept clear, because we are going to use it a lot in this topic. So, well, I'm going to open up, I have opened threads in the forum of the subject, so you can post your doubts about these things if you don't understand any concept. So we are going to continue seeing things. Well, this is quite obvious. If we have n variables, we can form 2 raised to n min terms and 2 raised to n max terms. Why? Because we are going to use the variables in its natural representation and the complemented representation. For example, if I have imagine that we have a function with 2 variables, the min terms that I can have here are these. Both of them negated, one negated and the other not. Sorry. It removed everything. So all the possible min terms are these. So just combining the variables negated and non-negated. So if we have 2 variables, we have 4 min terms. But we are going to have also 4 max terms, just doing the same thing. Just using the negation and non-negation version of the variables. So this is quite obvious. So we are going to assign a number to each minterm and to each max term. How? In this way, imagine that we have the minterm, imagine that we have a 4 variable function that has these variables. And we can have a minterm of this function that is this one, the one in the example. We are going to use a 0 if the signal, if the variable is complemented, and a 1 if the variable is uncomplemented, not negated. So for x1 is negated, we are going to have a 0. For x2 is not negated, we are going to have a 1. For x3 we are going to have a 0 because if negated, and for x4 we are going to have a 1. And this is number 5. So we are going to call this minterm the minterm 5. Okay? For the minterms we are going to use lowercase m, and for the max term we are going to use uppercase M. We are going to assign also a number to the max terms, but we are going to do it in the opposite way. Why? Because remember the duality principle. If we use logic products, we are going to use logic sum in the other. And if we use ones, we are going to use zeros in the other. So, for example, using this example, we are going to use if x1 appear negated, we are going to use a 1. Just the opposite as before. Negated version, a 1. Non-negated, a 0. This in the min terms. In the max terms. In the min terms is exactly the opposite. Okay? So in this example, x1 is negated, we use a 1. x2 is not negated, we use a 0. x3 is negated, we use a 1. And x4 is not negated, we use a 0. So we have built this number. This number in binary is 10. So this max term is the max term 10. Sorry, I have to use uppercase M. This is the max term 10. So just replacing the variables by zeros and ones depending on if they are negated or not, we are going to obtain the number linked to the min term and the number associated with the max term. So if I tell you now, for example, that we have a three variable function. I don't know why it's not right now. Imagine that we have this function, and I tell you, give me the min term 3. It's a little pain, this tablet, sorry. Obtain the min term 3 of the function. So 3 in binary is like this. So it's a min term. So if it's 0, the variable is going to appear negated. And if it's 1, it's going to appear non negated. Okay, this is the min term 3 for a 3 variables function. If I told you to obtain the max term 4, or for some, not 4, 6. 6 in binary is this. So a max term is a sum. So if it's 1, it's going to be negated. And is it 0? Not negated. So this is the max term 6, applying the equivalence. So you should know how to make this conversion, okay? If I tell you mixed term or max term 6, 7, whatever, you have to know how to express its algebraic representation. I think this is easy as well. So I know that there are a lot of concepts, but they are easy to understand. More things. Well, in this table we have a summary of all the possible min terms and max terms for a 3-variable function. So you can practice. You can practice taking the min term, the value, and converting this into this, just in the way that we have seen before. Okay? If you have problem with this, just let me know. I think this is easy. So more properties. Well, these properties are quite simple. I mean, if you have two Boolean functions, if you multiply or sum of negated them, the result is going to be also a Boolean function. This is quite obvious. Sorry. The De Morgan's theorem was one of the Boolean algebra theorems, so we don't have to repeat it here. We have a generalized De Morgan theorem, so you can obtain the De Morgan theorem applied to a function, just changing the variable by its negated version, the logic sum by the logic product, and vice versa, and the one for the zero, and vice versa. So it's quite easy. And here we have another theorem that I think that is, well, it's easy to demonstrate. I'm going to demonstrate it. The sum of all the min terms of a function is 1. So imagine that we have a 2-variable function, for example this one. So we have 2 variables, so we are going to have 4 possible min terms. So we are going to sum all the min terms of the function. So sorry. For example, using the distributive property, I can extract negated x from this expression, non-negated x from these two expressions. So I can make this. Okay, this is the distributive property, and we know that this is 1 and this is 1. Why? We are going to remind this theorem. Sorry, I have had, where is it? Here, the complementation theorem. You have a variable summing to its negated version is 1. So if we continue, we know that this is 1. So we have this. That is this. And applying the same action, the complementation action, this is 1. So the sum of all the min terms of a function is going to be 1. We have, as always, the dual property. The product of all the max terms of a function is going to be 0. I'm going to leave you this demonstration if you want. If you are interested, we can see it in a tutorial session. So we continue. Well, the Shannon expansion theorem is really important. Why? Well, I'm saying all the time that everything is important, but this is really important. at least if consequence. When we develop the Shannon expansion theorem, we are going to reach a conclusion that is quite powerful. So let's see. It says that we can express a function as a sum of two min terms as a product of two max terms. Always we have one expression and the dual. How? We are going to extract the variable of the function. We are going to extract the variable and we are going to put the variable here, and in its place we are going to put a 1, and in the other term of the sum we are going to extract the negated variable and we are going to use a 0 in its place. I think that the best way of seeing this is with an example. So I'm going to develop this here in a paper, in a blank page, to see it. So imagine that we have a two variable function like this. The variables are x and y. So if we apply the Shannon expansion theorem, we can make this function be the following. We extract the first variable and in its place we use a 1. And the second term of the sum is going to be the variable that we have extracted, negated, and in its place we write a 0. So I think that we can to expand the Shannon theorem for all the variables of the function, and that thing that we are going to do here. Now we can apply again the Shannon expansion theorem to these new functions, and that's the thing that we are going to do. So x is going to multiply the application of the Shannon expansion theorem to this function. So we are going to extract y, and it's going to multiply to the function, and in the place of y we are going to write a 1, and y negated, and in the place of y negated we write a 0. And now we are going to apply the Shannon expansion theorem to this new subfunction. So we have negated x that multiplies to all of this. We extract the y that multiply to the function, and in the place of the y we write a 1, and y negated, and in the place of the y negated we write a 0. So now we can develop this function. If we apply the distributive property, that is the axiom 4, if you check it, we can have x multiplying to this and to this. So we have x multiply y, function in 1, 1, plus x multiply y negated, and the function is this, and negated x multiplying to these terms, just the distributive property. Negated x, y, multiplying the function evaluated in 0 and 1, and finally x negated, y negated, and the function evaluated in 0 and 0. This is the result of applying the Shannon expansion theorem. We are going to apply the Shannon theorem to every variable in the function, but step by step. So now have a look at the function. Have a look at the terms that are multiplying the function. I'm going to remove this, not to avoid confuse the arc with the complementation. If you see, this is the min term 3. Why? Because the min term 3 in binary is 1, 1, and a 1 is to have the variable not negated. This is the min term 3 of the function. This is the min term 2. Why? Because 2 in binary is this. So we have s not negated and y negated. This is the min term 1. Why? Because 1 in binary for two variables is this. So first variable negated because of the 0, second variable not negated, and finally this is the min term 0, and again 0 in binary for two variables is 0, 0, that is both variables negated. And this is not a coincidence. This is not a coincidence. This is a consequence of the Shannon expansion theorem. So imagine now that we have a function whose truth table is the following. Because so far we have treated this function in a generic way. We don't know which is exactly the algebraic function. So the function of above is going to be that described by this truth table. We have two variables with these possible combinations, and I'm going to give you that the output is, for example, this for every combination. This is our truth table. What is the value of the function for the combination 1, 1? We are here. Is 1. What's the value of the function for the combination 1, 0? We are here. Is 0. For the combination of the input 0, 1, we are here, and it's 1. And for the combination of the input 0, 0, we are here, and it's 0. So we can replace these values here. Okay? And what happens? We are going to continue here. We have min term 3. I'm going to use the min term terminology instead of this, instead of the algebraic term. Min term 3 is multiplied by 1 plus min term 2 that is multiplied by 0. I'm just using the values here, okay? Plus min term 1 that is multiplied by 1, and finally min term 0 that is multiplied by 0. So if we continue developing the function, we have that the function is something multiplied by 1 is the same thing, and something multiplied by 0 is 0. You can check this in deduction and theorems. It's quite straightforward. So this is 0 and this is 0. So we have that finally the function is the min terms 3 and the min term 1. So we can reach a conclusion here. What is the conclusion here? The min term 3 and the min term 1 are those min terms that makes the function be 1. So the function is the sum of the min terms whose value is 1. Well, this is not exactly the notation, but are the sum of the min terms for which the function is 1. We have two variables. I don't know if this is clear, but this is quite powerful, because just looking at a truth table, we can have the algebraic expression of a function. I'm going to give you an example. Imagine that we have another truth table that is like this. Sorry, this is an f. So which are the minterms for which the function is 1? The minterm 0 and the minterm 3. So we know that the function is minterm 0 plus minterm 3. Minterm 0 is the product term, sorry, the product term, the minterms in which both variables are negated, and minterm 3 is the minterm with no variable negated, because this is 1 1 and 1 1 0 0. So with this conclusion that we have reached using the Shannon expansion theorem, we can go from the truth table to the algebraic expression of a function, just looking at the places of the table in which we have a 1. But we have the same for the zeros, because we have the duality with the max term. So which are the places in which the function are equal to 0? In the max term 1 and the max term 2. So we can express this function in an alternative way as the product of the max terms in which the function is 0, that are max term 1 and max term 2. It's just the dual principle. So it's a product of max terms. So if we have max term 1 is 0 1 and max term 2 is 1 0. Remember that we have to do the opposite. If we have a 0, the variable is not complemented, and if we have a 1, the variable is complemented. So these are two dual expressions. In fact, we have here a sum of minterms, and a sum of minterms is a disjunctive normal form. Remember from the slides. If we have a product of max terms, we have a conjunctive normal form. In fact, right now, with this, you know how to pass from a truth table to the disjunctive normal form of the function and to the conjunctive normal form of the function, just looking at the ones or looking at the zeros of the function. If you look at the ones, you are going to use a sum of minterms. If you look at the zeros, you are going to use a product of max terms. So this is really powerful, because we can make the transition between one representation and the other in a really easy and fast way. And now I'm going to introduce two more definitions, because these are not only disjunctive and conjunctive normal form. These are, I'm going to remove something of the screen. Well, I'm going to use just more space. We are going to use the canonical, we are going to introduce the canonical disjunctive form. And this is going to be a disjunctive form in which all the terms that appears are minterms, not product terms. If you remember the definition, the disjunctive normal form is a sum of product terms, and the conjunctive normal form is the product of various sum terms. If these sum terms and these product terms are mean terms, that means that all the variables appear, we have the canonical disjunctive and conjunctive forms. So the canonical disjunctive form is a disjunctive form in which all the terms appears. So we can define the canonical disjunctive form as a sum of the mean terms for which the function is 1, and the canonical conjunctive form is going to be the dual definition using the max terms. It's going to be a product of the max terms that make the function be 0. And we can express in a compact way this canonical form in the following way. In this case, f of x and y is the sum of a two-variable function of the mean term 0 and 3. Okay? Because it's the mean term 0 and 3. We can express the canonical conjunctive form in a compact way as the product of a two-variable function of the max terms 1 and 2. Okay? These are the compact representation of the canonical disjunctive and conjunctive forms of the function in the example, this one. Okay? Here we have, well, this is a little mess, so I'm going to remove this. We have the canonical forms algebraically and in a compact way, just indicating which are the mean terms and max terms involved. We are going to do more examples of this, but you have to identify these forms because you can be asked to calculate the canonical disjunctive or conjunctive form of a function in the exam or in an exercise. So we are going to continue. So we continue with the slides. Well, you have here the definition, the formal definition of the canonical disjunctive form and the canonical conjunctive form in red and blue for the sum mean terms, sorry, for the product mean terms, and for the sum max terms. So the canonical disjunctive form is the sum of all the mean terms for which the function is equals to 1. And the canonical conjunctive form is the product of max term for which the function is equal to 0. This is a way of putting this thing in a formal way, but behind this we have the truth table. We are looking at the one at the zeros, and we are going to extract the mean term or max terms depending on what we need in each occasion. So how can we obtain the canonical disjunctive form? For example, if we are given a function, we can apply the Shannon expansion theorem to obtain the canonical disjunctive form. You have here an example for a specific function. We are going to do this step by step in this sheet. So, for example, we have the function we have this free variable function that is x, y plus y, z plus x, y, z, and x and z negated. The first thing is to identify which is this representation of the function. We can see that we have 3 product terms, because we have 3 products of literal of the function, and they appear at most once. So if we have a sum of product terms, we have the disjunctive normal form. Why is not the conjunctive normal form? Because in the conjunctive, why is not the canonical? Instead of the normal, why is not the canonical? Because in the canonical, all the terms are mean terms. And here we have that these two product terms are not mean terms because we don't have all the variables in them. So the target of this exercise is to obtain the canonical disjunctive form using the Shannon expansion theorem. So we are going to use the expansion Shannon theorem applied to this function. So we start with the x, the first variable. We can extract the x and place a 1 in its a 1 in its place, and x negated and a 0 in its place. So we're going to do it. What happened? We're going to calculate this. Using the function that we have above. This is is the following. I just have put a 1 in the place of the x. So this is 1. Something multiplied by 1 is 1. Again, you can check here the properties. Here is the identity elements, okay? I'm going to leave here the slide in case we need it again. So this is a 0. Something multiplied by 0 is 0. So this is 0. And finally we have this. Okay? And now we are going to obtain this. So this is a 0, this is 1 because it's negated, and something multiplied by 1 is the same thing. So we have this. I think that everybody can see this. So we are going to replace this sub function here above. This set is negated, sorry. Okay, I'm going to remove this to have more space. So we can apply the distributive property, that is the axiom 4 here. And we have x that multiplies, we have this plus this plus x negated multiplying y negated and z, x negated multiplying y z negated. and this function is like it appears here. And we are going to call this, for example, the form of the function 1, the form 1 of the function. Now we apply again the Shannon expansion theorem, but now we are going to apply the Shannon expansion theorem to the following variable, that is the y. So we obtain these new sub functions. Okay? But we are going to start using the previous function. So we are going to be using the previous function that we obtained in each step. So this is the following. If we replace 1 in this function, in the y, we have this. Or we can do it directly, I think, just to be faster. This is y that multiplies well, I finally have decided to do it step by step because it's clear. So this set function here, replacing 1 in the place of the y, we have this thing, that is putting a 1 in the previous expression. Okay? So we have here 1 complemented is 0, so this is 0, something multiplied by 0 is 0. Here we have 1 complemented, so it's 0. Something multiplied by 0 is 0. So this is a 1, and this is a 1, so this term remains the same. So we have this. So here we have y multiplying this. And now we are going to calculate the other function. So we have x0 plus x0 negated z plus x0 negated z plus s negated 0 z negated. This is 0, this is 0, and since 0 negated is 1, this term remains the same. So we have this and this. So we have that here is negated y multiplied by this new sub function. I'm going to remove the previous expression to have a space, and we can continue developing the function. That is applying again the axiom 4, the distributive property, xy plus x negated y z negated. Note that I'm sorting the variables respecting the order x, y, and z, okay, when I calculate the function. Plus x, y negated z plus s negated y z. Okay, this is the second expression. This is x negated, sorry. This second expression. And we finally have to apply the Shannon expansion theorem to the second function, but this time using the z, the third and last variable. So again, we apply the Shannon expansion theorem, but this time using the z. and we have the following. Calculating the subfunctions, we have that this is xy plus x negated y1 negated plus x y negated 1 plus x negated y negated 1. So 1 negated is 0, so here we have 0, and the rest remain the same. x1 plus x1 negated plus x y, both of them negated, and the other subfunction is the following. Now z is 0, so we have xy plus s negated y 0 negated plus x y negated 0 plus s negated y negated 0. Remember that we are using the second expression that we obtained. So here we have a 0, so it's 0. Here we have a 0, so it's 0. 0 negated is 1, so we can keep those terms in the same way they are. So now we are going to replace this expression here. So we have z that multiplies xy plus xy negated plus x negated y negated, and negated z that multiplies xy plus x negated y. So again, I'm going to remove these two subfunctions to have more space. Applying again the axiom 4, the distributive property, we have that the function is x, y, z. I'm just multiplying this using the distributive property, and I am sorting the variables in this order. So plus x y negated z plus s negated y negated z plus, now in the other place we have x y z negated plus s negated y z negated. So this is the function that I have obtained. And now we cannot apply the Shannon expansion theorem anymore, because we have applied the Shannon expansion theorem to the three variables. So we have obtained the last version of the function. If you look at this expression, can you identify this expression? We have a sum of product terms, but these product terms are indeed mean terms because all the variables of the function appears. So this is the canonical disjunctive form of the function. Canonical disjunctive form of the function. Instead, we can calculate the mean terms implied. So this is the mean term 1, 1, 1, because all the variables are not complemented. So is mean term 1, 1, 1 is 7, because 1, 1, 1 is 7 in binary. This is the mean term 1, 0, 1. This is 5 in binary, so is the mean term 5. This is 0, 0, 1, so it's 1 in binary, so this is the mean term 1. This is 1, 1, 0. Remember that 1 is when the variable is uncomplemented and 0 when the variable is complemented. This is 6 in binary, so this is the mean term 6. And this is 0, 1, 0, that is 2. So it's the mean term 2. So we have the canonical disjunctive form. And if we want to express the canonical disjunctive form in its compact way, we know that is the sum, we put 3 because we have 3 variables, of the mean term 1, 2, 5, 6, and 7. We have solved the exercise. We have the canonical disjunctive form in its compact way and its algebraic way. Note that it's really easy to pass to the canonical conjunctive form. Remember that in the conjunctive form we use the max terms. So if the mean terms are those for which the function is 1, if we look at the zeros, we are going to have the max terms. Where are we going to have a 0? In the remaining positions. We are going to draw the truth table of the function using the canonical disjunctive form. We have 3 variables. With the 8 possible combinations. So we know that in these mean terms the function is 1. So we have a 1 in the mean term 1, the mean term 2, the mean term 5, the 6, and the 7. And the other combination is going to be 0. The other are going to be 0. So here again, yes, it's like this. So we can obtain the conjunctive, the canonical conjunctive form using the max terms. So the function is going to be also the product of the max terms, for which the function is 0. That is the max term 0, the max term 3, and the max term 4. Because this is 3 in binary, this is 4 in binary, and this is 0 in binary. So 0, 3, 4. But note that we don't even need the truth table, because just from this expression we know that we are going to have 0 in the numbers that doesn't appear here, that don't appear here. So in here we don't have the 0, we don't have the 3, and we don't have the 4. So we know that in these combinations of the input we are going to have a 0. So just looking at the canonical disjunctive form, we can obtain the canonical conjunctive form using the max terms. So it's really easy, using the consequence of applying the Shannon expansion theorem, to go from one form to the other of the function. You have to feel comfortable moving from one to the other representation, because this is crucial in the subject, and this is going to appear in the exam for sure. So let's continue. Just a thing, we have this function in its canonical disjunctive form, and in its canonical conjunctive form. I'm going to write algebraically the canonical conjunctive form using its compact way. So we are going to have 3 max terms. The max terms are some in which all the variables appear, and we have 3 of them. So 0 is like this. We have 3 zeros, so none of them are negated here in the max term 0. 3 is, so we have x non-negated, y and z negated, and 4 is this in binary, so we have the x negated and the other 2 non-negated. So this is the algebraic expression of the conjunctive canonical form. If we have to build the representation of the function using logic gate, what is better? What do you think is better? To use the canonical expression, the canonical disjunctive form, or the canonical conjunctive form? This is a thing that you have to evaluate from time to time, because maybe you have to save gates. Maybe one representation is cheaper than the other. For example, we are going to represent the logic representation, the logic gate representation of the canonical conjunctive form. So we have here a logic sum with 3 inputs. So a logic sum is an OR gate, and it has 3 inputs. We have here another OR gate here with 3 inputs, and finally another sum with 3 inputs. So here we have x, y, and z. Here we have x negated e, so we need an inverter, and negated z, we need an inverter, and finally here we have negated x, we need an inverter, y, and z. I don't know why this is not drawing. Okay, just give me a second. Here we have the sum of the 3 inputs. The sum of the 3 inputs, and the sum of the 3 inputs again. And these 3 sums are multiplied because we have here a logic product. So the logic product is made with the AND. Since we have 3 inputs, so this is the function implemented using logic gate and coming from its conjunctive normal form. I don't know if you have doubts, just tell me, okay, when you watch this. So we come back to the slides, and we have here the example that we have just seen. You have here all the steps if you want to check it, okay? And you have here the truth table, the canonical disjunctive form algebraically, also using its compact form, and the canonical conjunctive form in its compact way and algebraically. So we have seen so many things, so many ways of representing the functions. I think a lot of things. Just algebraically, we have all the disjunctive and conjunctive forms, the normal and the conjunctive. We have seen how to apply the Shannon expansion theorem. We have seen quite a lot about the Boolean algebra. So we know that we have several forms of representation. The circuit scheme, you know, those using the CMOS and the NMOS logic families. We are not going to work with any other family, just these 2. The logic gate diagram that we have seen just before, just connecting, OR, AND, etc. Inverters, whatever we need. The algebraic expression, we have worked a lot with algebraic expression in this lesson. We have enumeration methods, okay? We have seen the truth table. we haven't seen the value vector, but it's really simple. The value vector is just, for example, we have a three variable function, and it's just to use a vector in which we are going to put the value of the output. So since we have three variables, we are going to have the output for the h combinations of the input. So imagine that the output vector is like this. It means that in the truth table, for the combination 0, 0, 0, we have that the output is 0. For the combination 0, 0, 1, the output is 1. It's just copy the output of the truth table in a vector. So it's quite simple. We have seen as well how to use min terms and max terms to represent algebraic expressions using the canonical disjunctive form. You know, a sum of min terms where the function is 1 of the and the canonical conjunctive form in which we use a product of max term for which the function is 0, just looking at the truth table. And the last kind of representation that we are going to see is the Karnaugh map. In this topic, I'm going just to present the Karnaugh map. In topic 5, we are going to work a lot with the Karnaugh map. So this is going to be just a presentation. So imagine that we have a three variable function with this the following truth table. Imagine that we have this function with three variables, x1, x2, and x3. And the truth table of the function is the following. This one, for example. We can use the Karnaugh map. The Karnaugh map is a matrix. In which we are going to have a cell for each value of the output. For example, if we have three variables, we are going to have 8 combinations of the input and 8 values of the output. So we are going to need 8 cells. For example, 4 columns and 2 rows. And now we have to put here the variables of the function. Since we have 4 columns, we are going to put 2 variables, and since we have 2 rows, we are going to write 1 variable. Quite important. You have to order. Sorry, you have to place here. I'm going to remove this. No, shit. Okay. You have to put here the variables respecting the way in which they appear in the function. I mean, if x1 is the most significant variable, you have to put it before. Later, you are going to put x2 and finally x3. Okay? So the thing that characterizes the most, in my opinion, the Karnaugh map, if that they are going to sort the values of the input using gray code. Always. So you have to learn how to write in gray code at least the values from 0 to 3. So 0 in gray code is this, 0, 0. 1 is this, 2 is this, and 3 is this. And to number the rows, we only have 2 rows, so we can use directly 1 and 0, that is the same in gray code. So how can we do the equivalence between the Karnaugh map and the truth table. So this is the cell 0. Why? Because x1 is equal to 0, x2 is equal to 0, and x3 is equal to 0. So we are here. This is going to be the cell 1. Why? Because x1 is 0, x2 is 0, and x3 is 1. So we are here. So we put inside the cell the value of the output. When you use in the beginning, when you start using Karnaugh map, I suggest you to write in the corner of its cell the combinations of the truth table, because it's going to help you to make the correspondence between the truth table and the Karnaugh map. So this is going to be 0, 1, 0 is 2, 0, 1, 1 is 3, 1, 1, 0 is 6, 1, 1, 1 is 7, 1, 0, 0 is 4, and 1, 0, 1 is 5. So now, in the position 2, we have a 1. In the position 3, we have a 0. In the position 6, we have a 1. In the position 7, we have a 1. And in the position 4, we have a 0. And in the position 5, we have a 1. So we have built the Karnaugh map that corresponds to this truth table. You can, you can, if you want, you can make the same Karnaugh map using a different combination here. Here, instead of using the way of organizing the variables that I recommend, this one, you can, for example, put x3, for example, x2, and x1. But now, making the correspondence between the Karnaugh map and the truth table is going to be a mess, because well, the 0, 0, 0 cell is this, so I know that we have a 0 here. But what is the 0, 0, 1? The 0, 0, 1, x1 is 0, so it's here, x2 is 0, so it's here, and x3 is 0. So this is the 1. And you have to put here the value that corresponds to the 1. It's going to be more difficult to find the combination of the values of the input. So my advice, really important, respect this. We are going to start assigning the variable starting by the most significant variable, the most significant bit, and following with the rest. Okay? So what happens if we have 4 variables? If we have 4 variables, we are going to have 16 possible combinations. So we need 16 cells to specify the output. So we are going to have just a matrix of 16 cells. We organize the variable starting with the most significant and following with the rest. Now the combinations are going to be, we are going to have more combinations. This is 0, 0, 0, 0, 0, 0, 0, 1, 0, 0, 1, 1 is 3. So every time you build a Karnaugh map, just add this little number to help you locate the position in the table. When you gain searching experience, you are not going to need to do this. What happens if we are working with a variable, with a function, of 5 variables? What's happening here? Sorry. You have 5 variables. You are going to need 32 cells. What we are going to do is to use 2 Karnaugh map. Okay? We are going to use 2 Karnaugh map, and we are going to divide them. One in which the most significant variable is 0, and the other in which the most significant variable is 1. So if we have the truth table like this, so we are going to have here the first 16 combinations, and this output is going to be in this kind of map. And for the following 16 combinations, we are going to use the other kind of map, because in the first range we have that the x1 is 0, and in the other range the x1 is 1. It's not difficult, you just have to learn how to organize this in gray code, but you only have to learn how to count until 3, from 0 to 3, and to make the correspondence between the cells and the values in the truth table. If we have 6 variables, we are going to have 64 combinations. So you need 64 cells. We are going to use for Karnaugh map, dividing them by the value of the 2 most significant variables. This is strange. I mean, normally we are not going to find this kind of complicated function with 6 variables, but that it may happen. It's the same, but you have more Karnaugh map. Well, it's like this, okay? So, just continuing, we have that in the end we are going to use Boolean functions to design combinational circuits. A combinational circuit is going to be a circuit that implements a specific function, and we are going to have several outputs or just one output. We don't know the number of output in advance, and each output is going to be a function of the input variables. And this is going to be a function that has an equivalence, a correspondence with real life. For example, I don't know, maybe you have 2 traffic lights in a street, and here you have a pedestrian, and the pedestrian have here a button that he can press to activate the red light and make cars stop. So maybe one button can be X1 and the other button can be X2. So I'm just inventing this function, okay? Just using a real life example. So F is going to be the activation of the red light. If it's 1, the red light is activated. If it's 0, the green is activated and the cars can continue passing. So if one of the pedestrians press the button, they are going to activate the red light. So if the pedestrian of the right press the button, it activates the red light. If the pedestrian of the left activates the red button, press the button, they activate the red light. And if both of them press the button, they are going to activate the red light. I'm modeling the pedestrian pressing the button with a 1 and not pressing the button with a 0. If both of them are not pressing the button, so the red light is not going to be activated. It's a quick example. I just want you to see that the Boolean functions are related to real life. We are doing this for a reason. It's not just theoretical things, okay? Well, so all of this is to implement real circuits that are going to affect our daily life. We continue. Well, logic gates is a thing that we have already seen. So, examples of representation of function. The logic gate diagram. What is this? What is this function? Really easy. This is an OR gate. An OR gate is a sum of its inputs. And this is an AND gate. An AND gate is the complementation or the negation of the AND, of the logic product. So, Z is going to be the product of its input. This is the AND, but negated. So we have the function that this logic gate diagram implements. We can have the circuit diagram. This is the circuit diagram that implements the previous function. But we are not going to use this technology, so forget it. We are going to use just NMOS and CMOS. And I know that you know how to implement this. Placing this transistor in parallel, the parallel of the transistor is multiplied in series. We can make this example if you are interested, but I think that you already know how to do it. The algebraic expression, okay, we have obtained it before, and we have also the truth table, okay? So, well, let's do a quick example of this. Imagine that we have this algebraic expression. I'm going to open the okay, this. So we have that expression that is, if we remember this, we have this, now I'm asking you, is this a normal form of the function? We have seen two normal forms. The disjunctive normal forms, that is the sum of product terms, or the conjunctive normal form, that is the product of some terms. If we look at the function, these are product terms of the function. Okay, they are not min terms because not all the variables are there, but they are literals that are multiplied. So this is a product term of the function, and this is a product term as well. So this is a sum of product term. Is it the injunctive normal form? The answer is no, because it's complemented. Because of this is not a normal form. So imagine that I'm asking you to obtain a normal form starting with this representation. We are going to do it. The first thing that we have to do is to apply the De Morgan's law, because we have that complementation. So the De Morgan's law, remember that we have to respect the priority of the product. So we can break the sum, but not the product yet. So we convert this sum in a product, and now we can break this new complementation that we have. Sorry. And now, is this a normal form? It's a normal form? Yes. Is a conjunctive normal form, because it's the product of two sum terms. So we already have, in a really fast manipulation, a conjunctive normal form. And in fact, if we apply here the distributive property, that is the axiom 4, we are going to multiply this by this. You know, it's just the distributive property. We can have the following: negated 1 x1 negated x3 plus negated s1 negated x4 plus negated x2 negated x3 plus negated s2 plus sorry, not plus, yes, multiplied And this is a normal form or not? Yes, it's a normal form, but this time we have a sum of product terms. So this is the disjunctive normal form. So quickly we have translated the original function in its disjunctive normal form and its conjunctive normal form, just applying the actions of the Boolean algebra. That's the reason why they are useful. So now, to finish the topic, we are going to do two quick exercises. The first one is this. Exercise 1. We have this function. Which have 4 variables, a, b, c, d. And the function is the following. So, what we have to do is to simplify the function. And this means that we have to obtain a shorter form of the function using as few operands and as few operations as possible. Now you are going to apply here the actions and theorems of the Boolean algebra. And I'm asking you to pause the video and to try it. Why? Because there are a lot of ways of doing it, depending on the actions and theorems that you apply. There is no only one way. So I suggest you to pause the video, do the exercise, and later compare with the solution that I have selected. So now I'm going to solve the equation. But firstly, I'm going to ask you which is this kind of representation of the function. We can see that we have a sum of product terms. So this is a disjunctive normal form of the function. Note that we can have a lot of different disjunctive normal forms depending of the product terms that we have in the sum. So well, I'm going to look at the expression and I'm going to start applying some actions and theorems. Well, this is my solution. Here I see that I have one variable and the same variable negated multiplying another thing. If we look at the consensus law, we have that this can be simplified as this. We can get rid of the negated variable. So this can be simplified as this. Applying the consensus law, that is the theorem 7. Consensus law. So I'm going to continue. If we look now at the function, we can use the powerful absorption law. The absorption law tells us that we have something that is summing the product of the same something and another variable. We can get rid of the second terms. We can do this. And this is the absorption law. That is the theorem 5. And I told you that this was quite powerful. So I can apply this here because I have b negated twice. So I can do a plus b negated, removing this term and the other term. Sorry. Okay. And now, again, we can apply the consensus law. Where? Here. Because we have here a, and we have a negated multiplying a different thing. So we can get rid of this version. This is the consensus law, the one as before. So we can make this. Sorry. We can get rid of the a negated. And we can apply again the consensus law, but with the b. We have the b, and here we have the b complemented. It doesn't matter if the b complemented is the one out and the b uncomplemented is the one inside. We just need that both of them are not the same. One is complemented and the other is uncomplemented. So we can get rid of this. And finally, we have this. So you can see that starting from from here, we have reached here, and it's the same function. If you if you build the truth table of the function, you are going to obtain exactly the same output for the same combinations. It's the same function. The consequence is that this is much cheaper to build. Here, the function is just this. Sorry, it's an OR. It's a logic product, so it's an OR gate. This is the function. If we use the original function, we have, I'm going to do it just to compare. A inverted B, well, inverted. I'm not going to do it, but you can imagine, because in the tablet is not working properly, so it's a little mess. But you can imagine that implement this circuit with logic gates, you are going to need more gates. You are going to need 1, 2, 3 AND gates, 1 OR gates, 4 gates, and some inverters. It's going to be much costly. Now we are going to do another exercise. So, exercise 2. Exercise 2. We have the following function. It's a 3-variable function with x, y, and z as variables. And this is the function. We have to obtain the canonical disjunctive form. Which is the current form? The current form is a sum of mean terms. So the current form is the disjunctive normal form, and we have to obtain the conjunctive normal form. How do we do to obtain this? If you remember, we applied, maybe it's here, the Shannon expansion theorem here to all the variables to obtain the canonical disjunctive form. Okay, so applying the Shannon expansion theorem to the function, firstly using the x, later the y, and finally the z, we are going to obtain the canonical disjunctive form. But what happens? This is a process really slow. It's quite time consuming. I'm going to show you a trick to be much faster doing this. What do we need to have the canonical disjunctive form? We need to appear the mean terms. And the mean terms are those product terms in which the three variables appears. So we are going to do this. We are going to make some transformation, some algebraic manipulations using the Boolean algebra to have all the variables present in all the terms of the function. So the Shannon expansion theorem is a way of doing it, but it's slow. It works, but it's slow. So I'm going to show you a new trick. The function is this. We have two terms, the term A and the term B. We are going to start with the term B, for example. The term B is Y and Z. What is the variable missing here to have a mean term? We need the X. I think that all of you agree. How can we obtain the X? We can apply the complementation theorem. The complementation axiom. The complementation axiom tells the following. This is the axiom 5, if I remember well. Says the following. A variable summing to its complementation is 1. Okay. So I can multiply this by 1 because it's the same. And according to this axiom, 1 is the same of one thing summing to its negated version. I need here the X, so I'm going to include the X using the axiom 5 because this is 1. And now we apply here the axiom 4, that is the distributive property. So just applying the distributive property, we have that we can go from this to this. We have an extra term. Yes, we have an extra term, but now they are mean terms because we have all the variables implied. So the term B is solved. We are going to work with the term A. In the term A, we need to appear the Y and the Z. So the way of making the Y appear is applying again the complementation axiom. We need as well the Z. So we apply again the complementation axiom. Remember that this is 1 and this is 1. So we are not changing really anything. So applying the distributive property, we are going to obtain the following. Yes, we have gone from just one product term, that was the X, to 4 mean terms. But I don't care because we are looking for the canonical disjunctive form. So if I substitute the new two expression here, we have the following. sorry, the x has become this, is right there, and the second term, the b term, has become this. And now, if we have a look at the function, we can see that, for example, this term is twice. So, the idempotent theorem, that is the 3, the idempotent law, says that x plus x is x. So we can get rid of one of them. So finally, we have that the function is the following. And this is the canonical disjunctive form of the function because it's the sum of its minterms. We can get from here its compact representation. We have 3 variables, and we have the minterms 1, 1, 1, that is 7, minterm 7, 1, 1, 0, that is minterm 5, sorry, 6, 1, 0, 1, that is minterm 5, 1, 0, 0, that is minterm 4, and 0, 1, 1, that is minterm 3. Minterm 3. So, in its compact way is minterm 3, 4, 5, 6, and 7. So we have solved the exercise. Imagine that now they tell you that you have to obtain the canonical conjunctive form. So we are going to look at the zeros. If we have, imagine that we have the truth table, which are going to be the combination of the input for which the value of the output is 0, for the combination that are not here, because these combinations are those that make the function 1. So the canonical conjunctive form should be, in its compact way, the product of the product of the function of 3 variables of the max terms that are not present here, the 0, the 1, and the 2. So we have obtained this version in a fast way. And if we build the truth table, I'm going to build it quickly here. So which is the truth table? We can look at both the canonical forms. If we use the conjunctive canonical forms, we know that in these max terms the function is 0. So we are going to have a 0 here, in the 0, in the 1, and in the 2. And where we are going to have 1s in all the rest of the combinations. But we can look here in the canonical conjunctive form, sorry, canonical disjunctive form, in which we have the minterms in which the function is 1. So the 3, the 4, the 5, the 6, and the 7. So I hope that this has been useful, and this has been Topic 4. We have finished topic 4. You can start doing exercises. If you go to the virtual campus, topic 4, you have here some tools that I have uploaded. They are online tools. They are simplifiers of the Boolean algebra. So you can place here some Boolean expression or here, and you are going to have the simplification. And the web page specifies in every step the theorem that it has used. So it's really useful, both of them. You have in the topic 5 tab a list with exercise of topic 4 and 5. So you can start practicing. Don't spend a lot of time with the base conversion on this thing. It's more interesting if you center on the Boolean algebra exercises. You can check if you have the right solution using this web page. Okay? So that's all. Thank you for listening. Bye.